We're going to look at this number 5 on the annotation directions. And there isn't much explanation given. It's kind of self-explanatory, but I'll go over it real quick. And what we're asking here, or what I'm showing you how to do, is that your promoter region will be high AT by about 10 to 15 base pair, but each side of it, each region on either side of that high AT region will be a high GC region. And the middle one will be 10 to 15, and then the outer one might be a little longer, 10 to 20. So I've kind of made a kind of a fake one here. This would be the perfect example. Here is our high AT of 10 or 12 ATs, and here is 14 or 15 GCs on either side. Now this is 100%. In other words, very high AT if it's 100%. What you don't know is that the K12 is roughly 51%, I think, GC and 49% AT. So that's the average. And so anything that goes above or below 51 or 50% is considered high. So how high is high, though? That's really what you want. But I would say if you have one of these and you are over 50%, and so there are 14 here, so 7 is 50%. So if you were to get 8, then that could be considered, certainly 9, you would be high GC. So in other words, if you have 9 G's or C's in this region, that would be a high percentage. The same here. If you had 8 or 9 in this region, which is more than half, let's see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This one is only 12. It's the shorter AT region in the middle. So if you had 6 is half, so if you had 7 ATs here, you would consider that high AT. And the same over here, you would consider it high if it had more than if this one's the same as this one, so 7 is half. So if you have 8 or 9 over here, G's and C's, G's or C's, then you would consider this one high GC content. And so it doesn't take much. You just have to have a little bit over 50% if you get to 60% or something. So like for instance, if you have 12, all right, times 0.6, 7 is probably enough. All right, if you have 14 or 15, say we have 14 times 0.6, now you have 8, 8.5, so 8 or 9 is going to be considered high. Now, if we go and look at what it says here, this would be what we consider the promoter region. So the promoter region, what is the size of it? Well, it's going to have all 3 of these parts. So at least 30 base pairs, 10 in the middle and 10 on each side, up to say about 50. So our region should be between 30 and 50 base pairs. Here we have an encoding sequence for the lac I. So let's try and do this for our lac operon I gene, and we'll use this 178, and we will pretty much, we want to look at the promoter region, and we're kind of looking where? Well, it's going to be near the start codon, so it's going to be somewhere in this piece right here. So I'll just grab and copy that real quick, and we'll put it on our where we're working here, and I will put that here. Let's paste it in here, and it did copy our thing. So let's take a look here. Well, here we seem to have a lot of high A's and T's because that's where we thought our TATO was. Do we have, can we go out to about 10? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, if we count this region here, is this going to work? We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it's 50%. So it actually doesn't match our quite match our region, but let's see if we go somewhere a little further. We were looking for different ones here. Let's try this one. How many are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here there are 12, and 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 12 are AT. So that might be considered our high AT region. And what do we find next to it? Well, here's our problem. We have another high AT region right here that's going to throw a monkey wrench into our analysis, because there's 1, 2, 3, 4, 5, 6, 7. However, if we were to extend all the way out here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, plus 13, 14, 15, 16, 17, 18, 19. There we go. Even though that looks horrible, if you actually take this region, which is I think 19, I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 out of the 19 are GC. So technically, even though you have these 3 T's and these 4 A's here, that is high GC. So that's a high GC region of 19. Then we had our high AT region. Let's see if this region is also high GC. All right, let's go to there. 1, 2. Let's give it some more. I think we started here. So let's go to here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so that's 10. And we have 1, 2, 3, 4, 5, 6, 7. Oh, wait, here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, so 9 out of 1, 2, 3, 4, 5. No, that can't be right. 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 1, 2, 3, 4. Yeah, out of 13. So if we count that, that is also a high GC region. So yes, we can count that, even though it doesn't look like the structure we have. This region right in here is high AT. This region right in here is high GC. And this region right in here is high CG. All right, so depending on how you want to take it, but certainly this would be your promoter. So your promoter, I would say, is what we would call, according to the number 5's definition. All right, these definitions are not that strong, but if you were going to find the promoter, I would say it's right here. It's this gray area that I have said, and our high AT is in, oops, edit, undo, there we go. Our high AT region is centered around this piece, which is likely, could be our Tata box. Not certain, but it could be. And then we have GC regions on either side of it. So that's what we're looking for here. That's how you should do your analysis. Explain it in the way I just did here. Try to find a region that has about 10 or 12, up to 15 high AT, and then find 2 regions on either side of between 15 and 20 that are high in GC. You need to show that those regions that are GC are higher than the one are equal to the one that's AT. But that should tell you that that's definitely your promoter. Now the thing is, theoretically, why is this? Well, it has to do with flexibility and rigidity of the DNA molecule. The rigid part, which should be the AT, is where you will have your binding, and then you need flexible region around it for or stronger. It depends on the way you look at it. More flexible region for it to unzip, I guess is the way you might say it, around that. But the actual polymerase does not, the function of the TATA box is not actually to attract the polymerase. It's actually to make sure it only goes in one direction. And we aren't 100% for sure of the mechanism on how that works, but the actual attraction is more likely to be this entire region. In fact, it's a region like this whole thing with the ATs in the middle and the GCs on the ground. That's actually what's attracting the polymerase, not the actual TATA. The TATA part in the middle is actually designed to make for sure that it only goes in one direction. So very theoretical there, but you do need to find this and get your 10 or 20 on either side of your 10 to 15 ATs in the middle. All right, so that finishes that one. Before we go, let's take a look at the next one. Now, the next one, specific promoters. Now, most of your genes are going to be TATA, which are called Prinbau boxes or TATA boxes. Prinbau is the person who invented it, but unfortunately the guy isn't famous because nobody remembered his name. They only remembered TATA. So it's a TATA box. Now, in bacteria, you're going to find it at -10 or in that region, and this is the consensus, and then you're also going to find a -35 consensus that looks like this. Of course, you don't have to get these exact, in fact, you won't find these exact sequences. We certainly didn't find it in the I protein. You're unlikely to find the consensus in it. Realize the TATA box is just high AT. All right, it doesn't even have to have all A's and T's. It can have a C in it or a G in it or something like that. And the -35 sequence, which is 25 base pairs further upstream to the TATA, should also be there. It just might be a little bit more difficult to find, and it doesn't have to be exactly that far. And I give you lots of information here on how to get a feel for what's going on. That 10 and 35 is just an average. It is certainly not set in stone. The consensus distance is about 17 base pairs. So 15, 17, here they have it at 10 and 35 is 15, but most of the time it's about 17, or so. It can be more, it can be less. You just have to look. Now, some promoters contain one or more upstream promoter elements. You should also look for those. One of them is this at -42, which is a bunch of A's and then some pyrimidines. All right, so you might look for a set of A's that are at the -42, and then W's, which are A's or T's, at -52. You might look at that as well. I'm sorry, let's see, R is A or G, N is any base, yes. So you might look for these two as well to see if you can find any evidence of a -42 and a -52. It should be noted the above promoter sequences are recognized by RNA polymerase only containing the sigma 70. Now, there are other versions in bacteria of the RNA polymerase that substitute out this particular protein. The sigma 70 sequence or enzyme is not the only RNA polymerase. There are other versions that are besides the sigma 70, and when that piece is different, then you will be getting different core promoter sequences. It binds to different things. It doesn't bind to what we've been looking at. And so if there's any indication that that you have a different one, you might look at some of these later examples. Here is more of your TATA. This is the one that we expect, and the -10 TATA, the -35 sequence. All right, and then here is more of a consensus, which if you have any problems reading that, so between -31 and 6 is what you should see, and here's your TATA, or here's an alternative version of the same thing. Different papers created different subsequences. They have different information and different abilities to do it. Capital letters are strong, little letters mean maybe. You can think of it that way. So if it's a little a, it's like more often than not, it's an A, but it's not strong. If it's a capital A, it's very strong. All right, so that means very likely that it's an A. So you have a TA, something else, an A, something else, and a T. Those are the strong ones. So it's TA, A, T, with some pieces in between. That's kind of the way you would look at it. Now, sequences to be on the lookout at -10 and -35. The interesting thing is, we think of TATAbox and it comes at -10 and it has this co-sequence that comes at -35, and you can look for those. And it's actually the position that is important, not the letters. The other parts, the other holoenzyme, or I should say the other subparts of the RNA polymerase, like that can be substituted out for the sigma 70, they will bind to different sequences than TATA. And so if you think you have one that is different from TATA, you would look for slightly different sequences. So this next chart is if you think you have like something that is related to heat shock, in other words, temperature change. In other words, some genes get activated by temperature change, and in this particular case, if you think your gene is related to that, then you should have, instead of looking for TATA and this sequence at -35, you should look for something like this, all right, and this at those two positions, all right. Now, if you have a gene that is based on building the flagella, all right, for some reason it has its own protein that recognizes this sequence, and then nitrogen starvation. And I believe maybe this last one is the most likely for any of the operons you guys have. So this might be what you substitute the TATA out for yours if you think you have something that might sense something like nitrogen. All right. So or a gas, or it's sensing something in the environment having to do with it. So if you don't find a TATA, you might look for these as an alternative. It's hard enough, of course, to find the TATA sometimes. You saw how I had to do it. But if you're really not getting anything at all in the right regions, in the -10 and the -35, you might look for these. Now also notice that this last one here, the nitrogen starvation, says 6 base pair. That's the separation between them. So here, the TATA has 16 to 19. We had like an average of 17 above, or 15. All right, that's -10, -35, that's 15. And here the average separation is a little larger than that, 16 to 19. Here, this one is 13. So these are all very similar to TATA. Notice that this one is only 6 base pair. So in a way, this one's easy to find. If you find something close to that, and then just 6 bases, or just a few, probably less than 10 away, you find something like that, you've got one of these. So this one is pretty easy to check for, and this is the most likely one. I think with your operons, this is the only one that's not TATA that you should probably be looking for. I'm fairly certain we don't have any of your operons coding for flagella, though you could have heat shock. They could be heat shock, and I'm just not aware of it. Generally, it'll be TATA, or this one with a very outside chance of it being heat shock. If you read anything about heat shock in any of the papers, well, you might look for it. But I don't remember seeing anything heat shock related to the operons that we have. But I could be wrong, and if some of them are sensitive to temperature, then you should probably look for this one as well. Nitrogen starvation is a possibility for some of your operons. Now, finding the transcription start site is much more difficult, and I will do another video completely on the transcription start site. It's very hit or miss. You have to find everything else first. Of course, finding an actual RNA will tell you exactly where the transcription start site is. So in a way, this is very easy, or it's very difficult. But if you actually have a functional mRNA in the database, it tells you where the start site is. So I'll do another one on the transcription start site in bacteria, and then we will then I'll show you how to format all of your information together.